straightforward with you. Today we're going to have to take down a lot of little pieces of information. So I will try to make it as exciting as possible, but there's a lot of little things I don't want to overlook when we're talking about these basic algebraic limits, okay, or analytic limits. So just bear with me, okay? First things first, okay? Three basic limits, okay? And I would not write this right here. Let's just understand that B and C are constant values. N is an integer, okay? Write down this. The limit as x approaches C of B is B. The limit as x approaches C of B equals B, okay? If your function is just a constant number, show me with your arms, what does it look like? What's the y value everywhere? The same thing. So no matter where I ask you for a limit on a horizontal line, it's going to be the same. That's what that's saying. Okay? So the limit of a number is a number, is the same number. Okay? The limit as x approaches C of x is C. Essentially, whatever this is, we can plug that C value in for. Okay? Our identity function, y equals x, our x and y coordinates are all the same. So if I ask you for any limit on this line, it's going to be that value. The limit as x approaches 2 is 2. The limit as x approaches 3, bless you, is 3. The limit as x approaches negative 15 is negative 15. That's all that's saying. Okay? We know what this graph looks like. We don't have to draw it out. We can just think about all the x's and y's are the same. And then number 3, the limit as x approaches C of x to the n is C to the n. Okay? Essentially, all we have to do is take this C value and plug it in for x. I know that not all of us really like the x's and c's and a's and b's and blah, blah, blah. So we're going to do some examples to where you can see exactly what I'm talking about. But really, when we have simple things like polynomials, we can take our C value and we can plug it in for x. Polynomials are continuous everywhere. We don't have to worry about holes or breaks or anything like that. So we can just take our value right here and plug it into our function like we would if we were going to find the y value, and that's going to be our limit. Okay? Write it down. The limit as x approaches 2 of 5. What is it? 5. Okay. 5 is a horizontal line where all the y values are 5. Everywhere's 5. Every limit's going to be 5. Okay. Right? We're at the 2. Thank you. Okay. This is a question that should be the easiest question on your quiz. If this is a constant, even if it's e or pi or pi cubed, whatever it is, if it's a constant, say no. The limit as x approaches 2 of x. All we have to do is we get to take this number and throw it in here because it's polynomial. So what's our answer? 2. That's nice. Okay, one more. the limit as x approaches 2 of x cubed. Alex, what would it be? You knew I was even calling you?
Yep.
You could like read my mind. Okay. We plug 2 in for x cubed. 2 cubed is 8. Okay. As long as we're polynomial, we can take this number and we can throw it in. Okay. All right. Now, I don't really want you to write this down. Okay. We're going to talk through these. I know, because I think that a lot of them are fairly intuitive. Okay, so we just talked about these basic rules right here. Like these are like basic rules. Okay, well, what if we have like a coefficient in front of x, right? What if we have a coefficient in front of our function? Well, then that coefficient is just going to be multiplied to whatever you get for your limit. Okay, well, what if we have a polynomial with multiple terms? Okay, well, if we have functions that are either added or subtracted together, we can find those limits individually and then add or subtract those limits together. Okay, you were probably going to do that even if I didn't tell you that was a rule. Okay, same thing with multiplying and dividing. If we have functions multiplied together, we can calculate their limits and multiply those numbers together, or divide those numbers together as long as we don't have a 0 in the denominator. Okay? And then if we have something raised to a power, same thing, we can find that limit and then raise it to a power. Okay? A lot of these things, if I didn't talk about them, you were going to probably assume anyway, but at least we've officially talked about them. They are in your book if you need to reference them. Okay? But I don't think that it's worth our time to write them down. Okay. All right, so you are going to hear me talk about direct substitution quite often when it comes to analytical limits. And I've sort of already been hinting at it in our basic limits. Okay. Okay. So first of all, we can use direct substitution as long as we have anything polynomial or a rational or the denominator is not 0. Okay. When the denominator is 0, we have to go to plan B. And I'll tell you what plan B is. Okay. But basically what's happening is whatever we have for a limit, we take that C value and we plug it into our function. Okay? I've been talking about that with our basic limits, but now this is applying to any polynomial or any rational as long as we're not dividing by 0. So what I circled in blue, that's really what I would write down. Okay? I don't think you need all of the other words. Just make sure that, our denominator is not going to equal 0. Okay? But whatever we have, whatever x is approaching, we can take that number and plug it in. Okay? Answer me this. If I am graphing a function and I plug x into my equation, what does that give me? If I plug x into an equation, what does that give me? The y value. Okay? So if we're talking about polynomials and rationals where the denominator is not 0, we're talking about functions that don't have a hole there. Okay? Now I know that a rational could have a hole, but that would be where the denominator is 0. I know a rational could have an asymptote. That is where the denominator is 0. But everywhere else, they're nice, smooth curves. So when we are calculating limits, we're really just figuring out where that y value is because we know that that's the coordinate we're going to approach. Okay? Now, when we get into the whole denominator equals 0 thing, then it's a different story. But as long as we have a smooth piece, we can just figure out the y value, and that's our limit. Okay, so I want the limit as x approaches 3 of 3x plus x squared. Write it down. X plus x squared is polynomial. Turn to your neighbor and tell them what you think we need to do. All right, Owen says plug in 3, we get 18. This is a polynomial. We're approaching 3, so I can plug in 3, and our limit is 18. You don't even have to grab it. Figure it out by figuring out the y value. Okay? It is as simple as that. Okay, don't overcomplicate it. The limit as x approaches 3 of 2 over x cubed. Julia, what do you think our answer would be?
Plug in 3 again.
Okay, so what would we get?
2 over 27.
Okay, plug in 3. 2 over 27 would be your outcome when you plug in 3. You like that? Owen's excited.
Better than graphics.
Better than graphing, right?
Yeah.
Okay. Also, I want you to understand that it is also okay to use direct substitution if we have some sort of root function. Okay? So if we have a radical, what I have here in blue, we can still use direct substitution with any sort of root function. Okay? We don't have any like holes or anything. So as long as C is in the domain, we can use direct substitution if it involves a radical. Okay? I know it's kind of up there, but what are we going to have to be worried about for C being in the domain? Okay, negatives in which case? Like all of the radicals or specific radicals? You're arguing over there. Who won? Okay. The even radicals, we can't have negatives underneath. So if it's a square root or a fourth root, we can't have negatives underneath. Those are imaginary numbers. So just make sure that your C is in the domain. Okay? For example, we have the limit as x approaches 3 of the cubed root of 3x squared. It is safe to use direct substitution. Now, some of you may be excited about this. Some of you may still do it the pre-calculus way. But you are in AP Calculus. In AP Calculus, you don't have to reduce. You can leave it as radical 27, and both me and Mr. Griebel will not take off points. Now, if this bothers you, you go for it. You say that it equals 3 radical 3. But if you leave it as radical 27, you still get full credit.
I don't disagree, but why?
Oh.
Why is that not the
Why is what?
case? Why do you guys allow us?
Because the AP test doesn't make you simplify, so
Okay.
yeah. There's bigger fish to fry in calculus than simplifying. Okay? Ethan's not complaining. He just wants to. Okay. Now, if direct substitution does not work, you don't have to write this down. This is just kind of a reminder for me. If direct substitution does not work, then we have to go to an alternate method. And really, that's a lot of what we're doing for the next week and a half. What if direct substitution doesn't work? Okay? So the first thing I want to talk about would be a rational function. Okay? I've been saying, as long as the denominator is not 0, as long as the denominator is not 0, as long as the denominator is not 0, well, what if the denominator is 0? Not screwed. Write this down. Okay, so you're going to be in the habit of trying direct substitution. Okay? Because that's what I always want you to try first. But what happens when we try direct substitution? What do we get in the numerator? And what do we get in the denominator? Okay? This is actually a good sign. If you get 0 over 0, more than likely there is some sort of technique we can use to where we can still evaluate our limit. Okay? So, what is something we can do algebraically? We could factor. Our numerator can factor to x minus 2 times x plus 2. Okay? We kind of talked about this yesterday, right? What happens? We have our x minus 2 factors canceling out, which means what is occurring there? A hole. And if we have a curve with just a hole, we still might be able to calculate the limit, right? Okay, so now we have the limit as x approaches 2 of x plus 2. Now can we evaluate the limit? You betcha. When we plug in 2, we get 4. Let's go. What's happening is we have a line with a hole at 2, 4. So what we found is where the hole is. There's not a function value there, but the limit as x approaches 2 is where this hole occurs at 4. Okay. It's exciting stuff, people. It's exciting stuff. All right, how about this one? Write it down. Here's what happens when we use direct substitution. Like if we plug 0 in for x, what would our numerator be? Okay, and what would our denominator be? Thank you, Pierce. Max, I know you want to be a helper.
Wait, you say Pierce?
I did. Okay. And what did I say? We don't want zeros in the denominator, but if we have 0 over 0, we probably can do something algebraically. Okay? What algebraically can we do? We can't change the value of our expression, so we can't just square it because then it changes its value. You are on the right track, though. We do need to do something about that radical, probably, because it's creating that 0. We're not. That's gonna find us our x-intercepts. Okay. We need to multiply by something. And when we multiply, we have to multiply by 1, right? So our numerator and denominator would get multiplied by the same thing. What we need to multiply starts with a C. C-O. C-O-N.
Confidence.
Have confidence, yes.
Contract.
C-O-N-J.
Conjunction.
Conjugate! Good job, Caleb. Okay, that led us to conjugate, so it is perfectly fine. So, notice how we have a radical minus a number. We could also do this if we had a radical plus a number, whether it was in the numerator or the denominator. But our conjugate would be a plus b times a minus b. So I'm going to pick a. This is a minus b, a plus b. Okay, and we are in AP Calculus, all right? There are some algebraic steps we don't have to show anymore. You know that a plus b times a minus b is going to give you the difference of squares. So, a squared minus b squared would be that. And our denominator, really not so nice, but that's okay. Okay, well, how is that helpful? What happens in the numerator? Okay. Simplifies to x, which is helpful because we can cancel this out here. So now using direct substitution, we have 1 in the numerator, and when we plug in 0 to our denominator, we get square root of 1 plus 1, which is 2. We have a Same thing is happening in this graph. We have a hole at 0, 1/2. So direct substitution didn't work, but once we got it simplified, we could evaluate for that y value. Okay? Biggest part of your homework tonight, you're going to have to remember some algebra. Okay? Please make sure you practice these problems so you can brush up on those skills. Okay? All right. 2 more items left. Okay? The limit of a composition function. Okay? Here is something to where I bet if I didn't show you how to do it, you would be able to figure it out. Okay? But we'll walk our way through it just in case. Okay. Okay, So let's just not write anything down quite yet. Okay? F and G are functions. We can calculate the limit as x approaches c, and we can calculate the limit as x approaches L. Okay? Let's write this down. So write down the limit as x approaches c of f of g of x. Write that down for me. Okay. Will someone remind me how to do a composition? What do we do?
If you plug in a number and you put it in G and you take the answer and put that in there.
Okay, so we go to the inside first. We go to the inside first, plug in x, and your answer goes to the outside, right? So what I want you to do is first you're going to evaluate the limit as x approaches c of g, and that's going to give you a value. So whatever your outcome is, you're going to take that outcome and you are going to take that limit for f. And then that's going to give you some sort of value. Okay? So you're going to evaluate the limit of the inside function, and then that outcome gives you where you need to evaluate the limit for the outside function. Just like a composition. And like I said, I might not even have to talk through this with you. You might have just done that anyway. But it's nice to put the pieces together, especially when we're dealing with something like super funky like limits, right? You've never seen anything like this before. Okay? So go ahead and write down these two functions. Okay. And before we try a composition function, you're going to be given two functions, maybe a couple different times in your homework, okay? And they're going to ask you for like maybe 3 or 4 different limits. And so they might write something like this. Find the limit as x approaches 2 of f of x divided by g of x. Okay? So what you're going to need to do is you're going to need to evaluate those limits separately based on the equations above. Okay? So let's talk through this. As x approaches 2 of f of x. So that's this up here. What's the limit as x approaches 2 of f of x? 8. We do direct substitution to get our output of 8. What's the limit as x approaches 2 of g? Radical 2. Hey, and guess what? It's AP Calculus. You can leave it like that. You can leave a radical in the denominator.
You're joking.
I've been waiting so long.
Only world.
Well, you can look at
This is very
it.
exciting.
I was already doing the next step.
All right, let's do our composition.
I just don't find it hard.
I love this lesson. I have mixed feelings about this lesson. I feel like this lesson's really boring, but I love that I get to tell you. You don't have to simplify because you get so happy every year. Okay, so here's our composition. We got to start with the inside. So the limit as x approaches 2 of g of x. What did you say it was? Radical 2. So what we have is the limit as x approaches radical 2 of our outside function. So now the limit as x approaches radical 2 of f would give us 6. Yay! Okay. All right. We are going to do one more thing, and you'll recognize it from one of your quiz questions. It's either number 4 or 1D. I can't remember how your quiz was broken up. It was the 4th problem. Please write this down. This is the difference quotient. Okay? And we're going to find the limit of the difference quotient, and we're going to use this during Unit 1 and Unit 2. This is super important. Like super duper. Yes. Now, on your quiz, did you see that delta x? What did you have? Okay. I am probably going to do my examples with an H. But that delta x, those of you who are in physics, what does it stand for? Change in x. Okay? So when we get to Unit 2, that change in x is going to become pretty important. We'll use it as H for our work. Okay? But you're going to have a couple questions in your homework, and we're going to practice it again at the beginning of class tomorrow, where I ask you to evaluate the limit of the difference quotient. So, the function we're going to do, I'm going to keep it linear, is 2x plus 1. Okay. I feel like everything we've done today has been fairly basic. So this is going to be where you're going to have to use your thinker a little bit more. I don't really think it's that bad. It's just we got to stay organized. Okay? So the limit of the difference quotient, I'm just going to replace any delta x with h. Are you okay with that?
Yeah.
I think it's easier to do our algebra with. So, h. All right. So f of x plus h means you're taking x plus h and you're plugging it in wherever there's an x. Minus f of x. Please make sure you put it in parentheses so that subtraction goes throughout the entire function. All over h. The subtraction, a big issue on our quiz. Okay. So what we have is the limit as h approaches 0. Yes, you have to keep on writing it until we evaluate the limit of 2x plus 2h plus 1 minus 2x minus 1 all over h. Okay. So now we have the limit as h approaches 0. What happens in our numerator? The 2x's and the 1's cancel. If you do not get to here and have something to cancel out with your denominator h, you've done something wrong. Every time you're going to be able to factor out an h from the numerator and cancel. Every time. Now we can evaluate our limit. What's the limit as h approaches 0 of 2? 2. If you had some sort of like squared term in there, you would be left with something involving an x. Oh no, hold on. No, I'm good. Sorry. It is okay to have an answer involving an x. That might happen. Actually, it will happen on a couple of your homework problems. Okay? Plug 0 in for h to evaluate the limit, but if you're left with something involving x, that's fine. Okay? One thing before we close. What is x plus h the quantity squared? Okay, just checking. Thank you. Okay? Please attempt every single problem. If you get stuck, try your best. Check the answer in the back of the book. Check Calc Chat if you need some guidance. If you are ready to turn them in, that's fine. You can put them in the basket. Your quiz corrections are due Thursday, but you are welcome to turn them in any time before that.